As we start Unit 5, this is a very busy unit. There's a lot going on in this one. We're going to learn how to write equations and how to balance them. And then we're also going to learn about several different types of reactions and be able to identify and balance those and predict what types of products they will make. So there's a lot going on in this chapter, but let's start with how do we write chemical reactions. So we're going to start off with word equations. And when we start writing equations, it's important to know where we put different items. So a lot of the times, well, not a lot, every time, when you have a chemical reaction, you're going to see an arrow. And that arrow is read as a yield, it gives, it produces. So that arrow has several different names. And to the right of the arrow, you're going to put your products. So this is what's being made when you're doing a chemical reaction. And to the left of that, you'll have your reactants. So the reactants are your ingredients. They're the things that you need, that you add together, and the products are what you're making. So for instance, iron as a metal can react with oxygen in the air, and it will produce iron 3 oxide in this case, which is rust. So if you've ever seen anything that's rusted, that's iron 3 oxide, and that's made from iron and oxygen. So that's a word equation, and we're going to take this, this kind of formula that's all written out in words, and we're going to be converting the ands and the producing to different symbols. So when we say iron reacts with oxygen, you're saying iron plus oxygen. The produce is where our yield sign comes in. That's one of the names for that arrow. So there's our produces. And then the iron 3 oxide is a product, so it's over here on our right hand side as a product. So all we've done is we've taken this more of like a sentence format, and we've replaced it with and symbols, plus symbols, sorry, and with arrows. We're going to want to write the names of our reactants to the left, and we're going to separate, in this case we have 2, so we want to separate them with plus signs, and then on our right hand side we want to put our products, and if we have more than one product we would want to separate those with plus signs as well. In this example though, we just had one product. So let's do an example. We have everything written out in words here, and we want to convert it to a word equation. So we don't want to convert everything to formulas, we just want to put in and signs, and we want to put our arrow where it belongs. So we're going to start with hydrogen peroxide. Okay, so we're going to start there, hydrogen peroxide. And it says that it decomposes, so that means that it breaks apart. And it says to form. If you look back, form wasn't one of the names given as the arrow, but it is another name for that. So when you form something, it means you're producing that. So hydrogen peroxide is going to break apart, and it's going to form, notice it forms 2 things. Water, here's our and, so that's going to turn into a plus sign, and then we have the oxygen gas. So we're going to put water as one of our products. We're going to separate water and oxygen with a plus sign. So that would be a simple word equation that we could have. We're used to seeing more chemical equations though. Scientists, by general definition, we're very curious, but we also like shortcuts. So chemical equations are going to use the formulas instead of the written out words for our reactants and products, and that just takes a little less time as well. So here's what we would call a skeleton equation, and we'll define that here in just a second. But this is everything that we've just did. Here's our iron, here's our oxygen, and notice oxygen has an O2. We can't just say, when we wrote oxygen, when we write out the formula for oxygen, it's O2. So we're going to do a reminder here of our diatomic molecules. There are 7 of them, and I'll put them on our next screen here as a reminder. You may want to jot those down. And then this is our iron 3 oxide, and all we've done is we've converted them into their formula instead of writing out the words. So a skeleton equation is a chemical equation. The only thing with the skeleton equation is it doesn't tell us how much of our reactants or how much of our products we need. So we just know the general formula. We know that we need iron, we know we need oxygen, but we don't know how much iron, we don't know how much oxygen. So it would be like taking a recipe at home and you needed to bake a cake, and it said, all right, you're going to need flour, sugar, vanilla, eggs. It doesn't tell you how much of each of those you need, so your cake is probably, unless you've been cooking for a while and know approximately how much of each of those you need, might taste kind of interesting. So in chemistry, we definitely want to know how much of each item we need, and we'll talk about that when we get into balancing equations in the next video. If we know what the physical state of the substance is, then we would want to also include that into our formula. For instance, we knew in our one problem that we had oxygen gas, so we would want to include in our formula that we have the gas form of oxygen. And here are the main symbols you're going to be using as far as what state you have. You'll be using an S if it's a solid, like iron would be. Liquids, for instance water, you would put an L behind that. Oxygen gas, we'd want to put a little G in parentheses behind our oxygen. And then AQ is one, we will be using this one quite a bit because in chemistry we make a lot of solutions. So anytime you have a chemical that's dissolved in water, you'd want to put AQ behind it. It stands for aqueous. But it just means that it's dissolved in water. So here's our new chemical equation, and it gives the physical state. So we know that iron, we want solid iron. We know that we want the gas form of oxygen, and we know that iron oxide, the iron 3 oxide, is also a solid. If our chemical equation takes a catalyst, and a catalyst is just something that speeds up a reaction, then we would want to include that in there as well. A catalyst is going to be something that you write above the arrow. It's not, well, it can be a chemical that you have to add, but a catalyst isn't used up in the process, so it doesn't actually play a part in breaking bonds, and it's not going to bond with items, so it's just kind of there helping things along. Heat can be a catalyst. There are some reactions that won't work unless you heat them up. So for instance, if heat is something that's needed, then you'd want to, on your arrow, you'd want to write heat above that. And that just tells whoever's looking at your chemical reaction that this reaction isn't going to work unless you add heat. So it's just it's an important piece, but it is just informational. It doesn't actually play a part in the chemicals or writing the formulas, but it would be something we would need to know if we were actually going to do that particular equation in a lab. I'm going to use this extra space here, and I want to just review the diatomic molecules really quick. I know that the diatomic molecules, just something that's easily forgotten, but as you start writing equations you definitely need to know this one. These are atoms that will bond with themselves, so they'll never be singular. So for instance, when it says that you have hydrogen gas, you can't just say hydrogen. It has to be H2. Another one is oxygen. Oxygen is always O2. Fluorine, pretty much all of your halogens. So you have fluorine and bromine. Iodine, nitrogen is another one. Sorry, I should be putting 2's behind these. And then we also have chlorine. Now one of the ways that you can remember these is if you look at your periodic, well there's 2 different ways. If you look at your periodic table, alright, you have hydrogen here, which is kind of a loner, it's off by itself, but the rest of these form a number 7 if you look at where they're at on the periodic table, and there are 7 of them. 1, 2, 3, 4, 5, 6, 7. So that's how my chemistry teacher in high school taught me. If you can remember the 7 on the periodic table and then hydrogen, just, it's kind of an oddball. The other way I've heard these people remember them is by Hofbrinkel. So if you can remember Hofbrinkel, Hofbrinkel, Hofbrinkel. Just a weird little name. It seems to stick in people's head, but that would help to remind you of the elements that make up those diatomic molecules. The last thing that you have here, and I rewrote most of this before I printed them just because it is a little blurry, but this just gives you some really common symbols that you may or may not be using. You're not going to use them in every single problem, but you will be using, for instance, your plus sign, your arrow. You're going to be using a lot of your the states of matter, solid, liquid, gas, aqueous. No reaction we'll be using occasionally when we get into the different types of reactions. NR for no reaction. Those are really common ones that you'll see, especially throughout these videos.